Rights Limited, Ekam UK, Ekam India, and IC India. He has experience of designing both TBM and NATM tunnels. He founded Tunneling Association of India A members in 2018 and is currently holding positions of Chair of TAIYM. He is presently committee member of steering board of International Tunneling Association A members. He holds the position of Vice Chair of the Institution of Civil Engineers, Delhi NCR Committee. He has presented his work at World Tunnel Congress 2019, Tunnel Asia Conference 2019, Tunnel Talk Magazine, TIOM, BTSOM, on various other platforms. Once again, I express our heartfelt thanks to Sri Sandeep Singh Nirmal Garu for accepting our invitation and going to give this webinar. And on behalf of IGS Guntur chapter and Chapati Institute of Technology, Modarka. Thank you, sir. Now, I request Sri Nirmal Garu to start the webinar.
Good morning, sir. Thank you very much for the introduction. And I'm really glad to be here today to share some of the experience that I have had and to give an overview of NATM and TBM tunnel. So I would like to ask if I am perfectly audible or should I move myself to be more clear?
Sir, it is audible, clear.
Okay, thank you. Thank you very much. So I will continue. So today we will be talking about overview of new Austrian tunneling method and tunnel boring machine tunneling methods to do underground tunnel construction. There you go. So I'll just move to my next slide. So we will be beginning our conversation with why we should go underground, and then touching a little bit about India and tunneling activities going on in our country. Then what methods of tunneling are available across the world, and then moving to TBM and NATM tunneling methods. So I usually have this photograph in my presentations. If you have seen it before, then you know what it is, and if you are seeing it this time, then I would like to explain that working underground is not one person's effort. It has to be a team effort where people from geotechnical background, from structural background, from environment, from ventilation, from electrical, from civil engineering, from tunneling come together, and they produce a wonderful product, building structures underground and making the space available overground for public to use for other purposes. This brings us why do we want to go underground? Why are we exploring the space underneath the ground surface? As per the predictions, the world population growth is a phenomena that has seen few peaks in previous centuries when we started agriculture, and then another peak when the medical revolution came in. Further, when industrial revolution kicked on, and now we are seeing another peak, another drift in the population, and this time the population rise is much more in developing countries than the developed countries. So India being one of the largest countries is going to see a rise in population, and which will put a lot of demand on infrastructure to move those people, to to provide housing for them, to provide transportation networks, to provide developmental opportunities, healthcare infrastructure, education infrastructure, offices, and much more. So we can imagine that land being a resource, we have to utilize it efficiently to understand that wherever we put all these infrastructure are utilized to their maximum efficiency, and the space is still available for people to enjoy themselves, for recreation, for walking, for cycling, and other purposes. This brings me to my next slide, which which basically summarizes the points that I have just shared. That increasing urbanization in developing countries is a fact, and it is going to be rather um, increased in the rate in coming future. We have to provide cities with sufficient shelter for creating spaces for people to live, infrastructure for services, transportation systems, even water supply. You may be aware that we have many tunnels now which are under construction and under proposal, which will bring water to cities like Mumbai and to Vidarbha region, and much more. And there are many tunnels in Himalayas who carry water along with dams. Further, we need adequate sanitation. So we are building underground networks for sewage transportation and disposal. And there is then increasing pollution, and there are requirements to find out ways to dump this pollution underground. For example, nuclear wastes are packed in a secure manner and are then dumped into the underground tunnels. There are many other applications of underground structures which we can go on, but to give a little bit of idea how we can utilize the underground space, there was one of the pictures presented in European Construction Technology Platform. So we can see that we can have metro systems, as you can see with my pointer. Then we can have tunnels carrying water or sewage. We can have road network inside. We can have trains running through underneath the city. We can have large water tanks which can be put underground rather than putting on the top of the buildings. We have other communication and electrical signal cables running underground, and you can see that by putting all this below the ground surface, we can actually create spaces on the surface for people to enjoy and to celebrate the spaces around them. So we can create parks, we can create lakes, we can create playgrounds, we can create parking lots, we can create spaces for people to walk, spaces for people to gather and celebrate. So it opens up lots of opportunities in future to come. As you can see that there is a photograph of one of the parking spaces in the middle of a very congested city. So there used to be a multi-level car park, and you can see that there is hardly any space for vehicles to move, and it looks very congested. But one of the artist impression says that if we move that car park underground at the same location, then we will have so much of space to have open air restaurants, to have spaces for people to walk, and it looks so much better if we imagine this space without this big structure which can be put underground. Further, this is one of the work that has been done in one of the European cities. So you can see that earlier everything was overground, so that there was tram which were running on the road, there was a road in this market, and electrical cables running here and there. which nearly corresponds to what we have in many crowded urban markets in India. And later on, all this space, all these trams, roads, everything was put inside the ground and with the electrical cables. And now there are trees on the top. The surfacing has been done for people to walk, for people to cycle around, and some art sculptures which are installed there. So it looks completely different and very beautiful, which gives people a peace of mind by living in such space. India is a fast-growing market for tunnel construction. China is the largest market as of now, but India is also catching up, and there is a lot of scope for road and rail tunnels, which we are hearing in news very often. Then there are metro systems. We have around 30 cities where underground metro systems are proposed, and many of them are under construction as well. High-speed rail projects. We know that there is 22 kilometers of underground tunneling in Mumbai in high-speed rail. Then we have smart city concepts, hydropower tunneling, which holds the maximum share of tunneling projects in India, and water supply and sewage tunneling. As far as road tunnels are concerned, I have gathered some long tunnel, and which is already under operation now, and then Banihal and Kazipur Road Tunnel, which is also quite a long tunnel. And we know the road tunnels which are in Mumbai Pune Expressway, and there are so many road tunnels that are that exists around around us and are under proposal as well. Few examples of rail tunnels from Konkan Railway, from railway tunneling in Himalayas. For example, the Punjab Railway Tunnel. You must have heard of it. It's a very famous tunnel. It's the longest operational tunnel of India as of now. And then another tunneling activity which is being carried on in northeast states of India, in Tupul Infal section. So there's a lot of tunneling going on for various reasons across India, for rail as well as road transportation. Then we know that there are so many metro tunnels which are under proposal and under construction, like Delhi Metro, Lucknow Metro, Mumbai Metro, Jaipur Metro, Chennai Metro, Hyderabad Metro, Mumbai Metro, Navi Mumbai Metro, Mega Metro for Ahmedabad and Gandhinagar, Kolkata Metro, and much more. I mean, there are so many to name. So there is a huge potential and huge way forward. Then we have high-speed train, which is already under proposal, and there we have a few underwater tunnels proposed into it, and other form of tunneling as well. Many tunnels between Ahmedabad and Mumbai, and long tunnels in Mumbai to reach to the main rail station. Then we have smart cities mission, which is to build smart cities in India, and and each smart city is going to have its own efficient transportation system. Most of them will have metro systems proposed for them as well. Then we have then we should move to the methods of tunneling. There are various methods of tunneling in India. Uh, there's some of them are open face methods, some of them are partial open face methods, cut and cover methods, mechanical excavations, inverse tube tunneling, jackbox tunneling, pipe jacking, micro tunneling, horizontal direction drilling. So in open face construction methods, we have manual excavations with timber headings. We have open face excavation with linings like steel graphite iron, steel linings, iron linings, etc., which was very common earlier in European countries. We have drill and blast technique, which is a part of NATM or SEL methods of tunneling as well. Then we have partial phase boring machines like road headers, shield tunneling, and full face excavations with use of tunnel boring machines as well. Today, we will not be discussing all of them, but we will be focusing more on NATM method of construction and constructing tunnels with TBM uh, methods. So we will first focus on NATM tunneling methods. NATM stands for New Austrian Tunneling Method, which was developed in 1950s by uh, Austrian tunnelers, and it what it signifies is that it is a flexible and observational approach. To explain what exactly it means, I would like to go back to the history of why this method was developed. So in early 1900s, rapid industrialization was going on, and every country was investing lots of money to bring resources from the uh, from the backward, poor, or uh, developing countries, which were colonized by the European countries, and to bring that material to develop industrial activities in their own countries, which later led to world wars. And by Second World War, every country has lost a lot of money, and industries and economic structures uh, were shaken due to the huge investments put on into the war and the destruction that was caused. Now, to carry on with the developmental activities, tunneling was already recognized in Europe as one of the way to go forward. But tunneling was an expensive activity, and there was a need to reduce the costs of tunneling. So in Austria and in other parts of the world as well, uh, efforts were made to find out a way to reduce the requirement of concrete and steel linings in the tunnels. So in 1950s, these researchers and these professionals found out a way that rather than considering that all of the ground load will come to the tunnel linings as after the excavation, they found out that ground has the capacity to support itself as well. So when we excavate for constructing the tunnel, the ground starts to move, and during the movement, it redistributes the stresses generated after the excavation, which means the surrounding ground starts to balance the load with the arching effect, and uh, and not the complete load is transferred to the lining, but the residual load, which the ground cannot take, is transferred to the lining, which means the linings can be thinner, and cost of tunneling can be reduced. So this is what it means, that it is a flexible and observational approach. So they propose that while tunneling, we should dig the ground. We should observe that what type of ground is lying ahead of us on the face of tunnel, and then we should decide what support we should apply to the ground according to its load carrying capacity. It is flexible, as in after each round the ground has to be assessed, and then we have to understand that what how much support is required to go into the ground. A flexible method gives an advantage to reduce the support where it is not required. Then later, Muller and Fecker from Germany published 22 principles of to fully describe the NATM. But with these 22 principles are explain more or less what we discussed now. So it covers that were provided by Muller and Fecker. You must have heard other names as well, such as SCL, short heat lining, and may sometimes confuse what's the difference between NATM and SCL. So SCL is an English concept because since England is majorly clay in terms of geology, the clay it's difficult to understand while excavation how clay will behave in long term because it will keep on deforming itself for years to come. So England planned tunneling in a way that they consider that all of the load comes to the lining. So the main difference between NATM and SCL tunneling is that SCL considers that complete load of ground is transferred to the tunnel linings, whereas NATM considers that only the residual loads are expected to come on the lining. So since England had, again coming back to the economics of it, since England had money and was rich, so they could design tunnels with full load of the ground, whereas NATM was followed in other parts of the world. As I have already discussed SCL, NATM is known with other names as well, such as conventional tunneling, drill and blast, sequential excavation methods, and many more. But they are more or less the same, except for minor modification proposed by each country or each professional which they have found during the tunneling process. To explain what is New Austrian tunneling method, I would like to show you a video from YouTube. So I'll share another screen, and please let me know if you can hear the video and see the video correctly. So I'll just find out. Yeah. Please stop me if the video is not being played correctly. If there is any, if you cannot hear the audio or the video is not.
Yes, sir, it is good. It is visible, sir.
The NATM, a standard method for building tunnels in mountainous areas, uses the geological.
Hello. Yeah. Can you see the video?
Yes, sir, it is visible and it is audible, sir.
Okay, I'll go on then. Thank you.
Stress from natural ground around a tunneling site to build a tunnel safely. In the construction of the Chuo Shinkansen, this method is used primarily in mountainous areas. The NATM uses machines and explosives to excavate natural ground. When using explosives, a machine called a drilling jumbo is used to drill into an excavation surface and fill it with explosives. Soil generated by blasting is carried off-site using a dump truck or belt conveyor. After excavation, concrete is sprayed onto excavated areas to reinforce natural ground. Rock bolts are then used to integrate the tunnel into natural ground. Depending on the conditions of the natural ground, arch-shaped steel material is used for reinforcement. This enables safe and efficient construction of a tunnel integrated into natural ground, using the geological stress of surrounding soil. excavation work can proceed at the front, while finishing work follows along at the rear. Firstly, waterproofing sheets are laid to mitigate the impact of groundwater. Next, lining concrete and track bed concrete are applied in that order. Tunnel construction is completed through these processes. The tunnel of the Yamanashi Maglev line, which already offers passenger rides, was also built by the NATM.
So I hope this gives an idea of how the tunneling by NATM construction is carried out. So I'll continue where I left. So what happens is when we go into the ground, we provide different type of supports such as shotcrete, rock bolts, lattice girders, and sometimes stiffer supports like pipe roof umbrella and stabilize the ground. And these all supports are called primary supports. Later on, we finish this primary support after putting a waterproofing layer. We put a permanent lining, which is the permanent support, which is durable for the project life of the tunnel, which we can say is nearly 100 to 120 years. So the excavation can be carried out in as a single phase or multiple phase excavation. If it is a smaller tunnel, then we can go for a single phase excavation, and if it is a larger tunnel, then we can imagine that excavating such a huge volume in one go may destabilize the ground. So we have to go for multiple phases. Along with the area of excavation, the geology also plays an important role. So if it is a weaker ground, then we have to divide our excavation phases so that we stabilize each pocket while we move forward. And if it is a competent ground, we can go for full phase excavation. So all this is analyzed while the design is made, and the excavation phases and support systems are worked according to that. So we can see that either it could be a single phase excavation, or we can do excavations in invert benching and heading, in multiple drifts, in side drifts, or we can do a pilot access tunnel in between first and then enlargement to the size of the main tunnel. When we design NATM tunnels, what we do is in softwares we simulate the excavation and support steps, and in step 1 we generate the in situ stresses of the ground, and generate the overburden loads if there are any over the tunnel. Later on, we simulate the excavation, and we see how the ground is moving. So you can see that this pattern of colors shows the displacements around the tunnel. The red color means that the ground is moving downwards, and blue color means it is moving upwards. And the intensity of the color shows how much the ground is moving. So you can see that maximum movement of the ground is on the crown of the tunnel and the invert of the tunnel. And this movement is understood by the behavior, by the capacity of the ground to deform. So we know that while the ground deforms, it has an elastic limit of deformation until which we can say that the ground will not fail. And after a limit of deformation, it will move to the plastic stage. And that's where we assume that the ground has failed, and we do not want ground to move any further. So in all these design simulations, we understand that when and how much support do we require to stop ground to be plastically deformed. So you can see that in this photograph, along with the displacements, we have put some rock folds and some shortcut to understand that uh, whether the ground will be stable during excavation. Now, when this all is calculated from the design, then we need to understand how to implement it on the site. So to implement the same behavior, to understand that what we have done in design is actually overlapping with what is going on at the construction site. We monitor the tunnel excavation throughout the construction after every excavation advance. So we put some displacement markers along the profile of the tunnel, and we can see that there are 5 markers here across the tunnel profile and how they are moving with time. So you can see that the readings were taken on different times and how they were moving after the excavation. So this depends on how the field stresses are present on that point of the ground, and we compare these displacements to the displacement that we thought we will be achieving during the design phase, and we compare if the proposed support system is sufficient, or we need more supports, or we need to reduce the supports during the construction phase. So after each advance, a geologist has to go to the site, to the phase, to understand what type of rock is there, and reassess the designer's recommendation on the support and if there is any modification required in the support itself. So moving on to the next slide. Apart from monitoring the deformation on tunnel profile, the deformation in urban areas, it is important to measure the deformation on the ground as well. So when we start excavating the tunnel, the effects of the movement of the ground uh, are shown on the ground surface as well, which may lead to differential settlements of the buildings or any underground tunnel nearby to the proposed excavated tunnel, or any utilities around it, maybe a gas pipeline or a water pipeline or a sewage channel. And due to differential settlements, they may crack and these structures may lose their integrity. So we need to monitor the surface settlements as well, and we review the support requirement of the tunnel if we are crossing the surface settlement limits as well. So if in case the settlements are large, we increase the support system, we increase the length of the rock boards, number of rock boards, short gate thicknesses, lattice girders, pipe umbrellas, anything which would bring us back to the same stage of construction. And this phenomena of surface monitoring is equally applicable for TBM tunneling as well. Moving on, this brings me to the TBM tunnels now. And somebody once said to me that tunnel boring machine is not just a machine; it's an industry in itself, which is actually true. It is wonderful to see how so many mechanical, electrical, and civil concepts come together to create this machine. And there is in the name of you, there is a cutterhead on the front of the steel which is so hard and robust that it cuts the ground of all the types. Even one of the hardest rocks can be cut using TBMs now continuously throughout the year, and it can go on for years as per the design, and which brings us to notice that how robust this machine is. Then we have a shield We have automatic shield. We have shield which stops the flow of water across the tunnel, which provides seal across with the ground and gives the grouting across the tunnel line. Then we have automatic segment erectors on the back, which are robotic arms which construct the segments on the back of the TBM machine automatically. Then we have automatic muck removal system, with the muck which is being digged on the face is taken out of the TBM and then it is taken out of the tunnel portal, and automatic transportation of segments from the tunnel portal to the TBM cutter head as well. Then we have various electrical systems which is powering this huge machine. We have ventilation system. Since we are underground, we need particular oxygen level and maintain low concentration of poisonous gases. An efficient ventilation system is the way to go in that scenario. And this ventilation system is automatically monitoring the air quality at various locations in the dams. So it's actually 100 to 200 meters long, and it has so many components that it wonders how everything is coming together and how it is producing such a wonderful product. As I have already explained a few components of it, like we have a strong robust cutter head on the front, then we have front shield, which does not allow the ground to collapse just after the excavation. Then we have main thrust cylinders, which push against the TBM lining so that the machine can move forward. Then we have torque cylinders, which move the motor of the cutter head. Then we have telescopic shield, which monitors where the alignment of the TBM tunnel is going. So if the TBM tunnel is deviating from the proposed alignment, it signals the operator that they need to modify the radius of the tunnel so that the machine can move in the right direction. Then we have dipper shield, which allows a seal between the ground and the tunnel so that the water does not come in and the grout material, the cement grouting does not come inside the tunnel. Then we have the erector, which is automatic robotic arm, which erects these segments to complete the lining, and then we have the segmental lining at the back. So to explain this, I have another video from Crossrail, and I will show that with the YouTube link that I have. There we go. Please bear with me for a second while I put it on. Use this one. And this video will show us the working of two types of TBMs, which I will be illustrating later. There are many other types as well. But it's a very comprehensive video which will explain the amount of work which the machine does while constructing the dam.
When it opens in 2018, Crossrail will connect 28 existing stations to the West End, the City and Canary Wharf through 21 kilometres of new twin-bore tunnels under central London. 8 tunnel boring machines, or TBMs, will drive through the ground to create Crossrail's tunnels. A TBM is 148 metres long and weighs 1,000 tonnes. This is the equivalent of 14 London buses end to end and a staggering 143 buses in weight. It has a rotating cutter head at the front and a series of trailers behind housing all the mechanical and electrical equipment. There are 2 types of TBM being used by Crossrail: earth pressure balanced TBMs and mix shield TBMs. 6 earth pressure balance machines will be used for the 18 kilometres of tunnel through the clay to the west and the riverbed deposits in the east, while 2 mixed shield machines will be used to drive the tunnels through the chalk beneath the River Thames. Depending on the geology below and the buildings above ground, each TBM will travel between 90 and 150 metres each week, ending up to within a millimetre of where it needs to be. The first part of the TBM's work is the tunnelling phase. The earth pressure balanced TBM has a cutting wheel which is pressed against the tunnel face by hydraulic cylinders. Inside the cutting wheel, the disc cutters and scraping tool loosen the material. If the earth is unstable and to stop the tunnel face collapsing or digging too fast, the TBM uses the soil that has already been dug out by the cutting wheel to support the tunnel face. This creates a stable environment for the tunnelling to move forward. The tunnel face is continuously monitored by pressure sensors. They check the turning power of the cutting wheel and the screw conveyor, and they also keep track of the material that's been excavated. The material is then taken away on conveyor belts. Once the tunnelling phase is done, the cutting wheel and screw conveyor are stopped and the ring building phase starts. A complete tunnel ring consists of several lining segments made of pre-built reinforced concrete. These are made in a special factory above ground. They must match the exact size required and are taken into the tunnel on flatbed rail cars. The concrete segments are fed in by the segment feeder and lifted into place using a vacuum. The hydraulic cylinders are temporarily retracted in order to provide enough space for the new segment. The segments are positioned with millimetre precision and held in place by cylinders before being finally bolted into.
Yes, please.
Sir, the video is breaking for a while, sir.
Okay, I'll just try to share it again.
Okay, sir.
To position.
Is it better now?
The conical keystone is put in from the front
sir, yes,
to
sir, it
complete
is
the lining ring. Each individual tunnel ring is built in a slightly conical form. This means that curves can be built along the tunnel route by changing the direction of the cone. The hydraulic cylinders are extended again to secure the segment into position. During all this work, the people and machines are protected by the shield skin from the saturated ground where water is under pressure. All the readings are displayed on monitors in the central control cabin and fed back to the machine operator. Once each section of ring building is completed, the next tunnelling phase can start. The mixed shield TBMs dig in a different way to the earth pressure balanced TBM and will be used for tunnelling in waterlogged conditions such as below the Thames. Mixed shield TBMs use bentonite, which is a slurry of clay and water, to support the excavation face and act as a suspension medium for excavated material. The excavation chamber is behind the cutting wheel and separated by a submerged wall from the working chamber. The excavation is completely filled with bentonite and the working chamber is approximately 2/3 filled. The two chambers are connected in the form of communicating pipes via an opening in the submerged wall. A filter cake is created ahead of the cutting wheel by pressurizing the bentonite in the working chamber with compressed air. The bentonite penetrates the ground to form a membrane which holds back water. Changes in the soil can be handled by adjusting the pressurization. The dugout material falls into the excavation chamber. Small grains are dissolved into the bentonite and bigger stones and debris fall to the bottom. Flushing nozzles guarantee smooth removal of the excavated material. The excavated material is pumped through the suction line to the separation plane at the surface. Here, the soil is separated out and removed from the bentonite suspension through a centrifuge, and the clean suspension is transferred back into the slurry circuit. As tunnelling advances, the flexible extension lines are installed to extend the lines after each thrust phase. Crossrail's first pair of TBMs, Phyllis and Ada, will construct Drive X, travelling from Royal Oak to Farringdon. A second pair of TBMs, Elizabeth and Victoria, will construct Drive Y, starting from Limo in Docklands and heading under central London to Farringdon. A further 2 TBMs, Mary and Sophia, will construct the tunnels for Drive H, running underneath the Thames from Plumstead to North Woolwich, followed by Drive Z and Drive G. All the tunnels will be completed by the end of 2014, a significant milestone in the programme to build the largest addition to the South East rail network in 50 years.
I hope the video was self-explanatory, and we found that the how EPB and slurry TBMs work and how are they. There are other forms of TBMs as well. I will move on to explaining those. So we already know about earth pressure balance machines, slurry machines. There are special machines to work in hard rock, because you can imagine that the transportation of loose material and hard rock material is different, and excavation as well is different from the TBMs. So they are customized for hard rock, which are called, some of them are called as gripper TBMs as well. We have compressed air lock TBMs, which are specially made for underwater tunnels, or tunnels where the water pressures are very high, such that the the front chamber of TBM has to be air locked, so that the water doesn't come in. Then we have station TBMs, rectangular TBMs for underpasses. Moving on to the hard rock or deeper TBM, you can see that this TBM it looks more or less like the other TBMs, but the main difference between this TBM and those TBM is that there is the shield on the back is not too long, because the rock is considered the rock TBM is considered to be operational in hard rock stratas, where we are assuming that the strata is self-standing, and after excavation the rock will not fall. Later on, we have these grippers, these red grippers, in which after each excavation, these grippers will grip the ground, and the TBM will be pushed against the force which we generate after gripping the ground. And then we do not have any TBM erectors on the back, because maybe there is no need of TBM lining. This TBM has a spray concrete facility on the back. Here, this spray will spray the concrete, and there will be no need of segments. It will just be the sprayed concrete, and the tunnel will be finished. So it's a unique TBM, and this was used in Gotthard Tunnel in Switzerland and many other tunnel projects as well. Then we have talking more about the hard rock gripper TBMs. These you can see that the cutter head for hard rock TBMs are different than the cutter head which was shown in video, because they have for the hard rock we have the round disc cutters at the front, so that they push the hard rock as a point load and break the rock in the front. You can appreciate better with this figure, where you can see that each of these discs are producing a normal force on the ground, and this normal force is crushing the zone in front of the cutter head, and thus leading to fragmenting of rocks and then collection of rock and transportation later on. And a beautiful image which you can see in front of TBM. You can see that all these discs create a circular pattern, and it looks amazing. And you can see that there is a band of band of white rock in between. There is a filling in between this gap, and the rock is quite intact. Moving on to compressed air TBMs, you can see that there is a airlock, a manned airlock. In this airlock is fit on the front part of the TBM, and if there is an intervention required, a person can go in, and the pressure are raised more than the pressure of the water outside, so that the water does not come into the airlock, and people can work there, do interventions to the TBM, change the cutter tools if required, if there any servicing or maintenance to be done to the TBM, and then come back. There are guidelines of how people can go inside that much of pressure and when they have to come back, so that it is safe for them to construct, to be there at the compressed air construction site. Then we have recent innovations in China and Singapore to construct the specialized TBMs for stations. So these machines are specially customized to create tunnel boring tunnels with a wider cross section for stations where there can be track of trains on the middle and then platforms on the side, thus reducing the requirement of a bigger TBM and saving lots of money due to excavation costs and the operation cost of TBM. Then we have rectangular TBMs, which are already working in China and Singapore, and now they are increasingly in demand. So these rectangular TBMs are usually uh, used for construction of underground underpasses, where there is a limitation on the space for doing the for sending the big machineries in and taking the muck out. So these take less space, and they do the rectangular cross sections for the underpasses as well. Which brings me to the nearly the end of the presentation. I have tried to summarize the uh, overview of TBM and NATM. There are a lot more details, and I think each slide can be explained in an hour or two. And if we go into the if we go into the detail, and I think for today we will keep ourselves for the introduction of what these methods are. And before concluding, I would like to share a little bit on what's the comparison between TBM and NATM, and when we should use them, when we should choose which one of them should be the right way of going ahead. So as we know, NATM is a very flexible method. There are small machines working, doing their small parts, and then finishing it in finishing it with other small machines as well, which makes it a very flexible method to be used in any location of the world, whether it is steep mountains or whether it is underground, underwater, anywhere. But there are complications with NATM when the ground is not very good. Then provide we need to invest lots of money to support the ground, uh, and it may become very expensive. The pace of excavation, the progress of project may also go down. But in that case, TBM can be helpful. At the same time, TBMs have their own limitations as well, because they are large machines. They need to be transported from various parts of the world to the project site, and transportation is not that easy when we are talking about tunneling in Himalayas or other hilly regions. Whereas when as you know that for slurry TBMs, we need a lot of space for slurry treatment plant as well. We need larger space for launching TBM tunnel also, because we need to prepare the whole launching facility at the back of the tunnel so that the TBM tunnels can move forward. So this cost benefit analysis and the geographical location, geology of the project is studied before making the decision to go for TBM or NATM. Although both these methods have been proved exceptionally successful in the industry, and uh, they have been proving themselves very useful for the industry in their own domain. So I think I'll conclude my presentation for today with this, and now I'll be taking some questions. So please share your questions on the chat box. Uh, I I already have few. I would like to know from the organizers if uh, if if we are ready for questions.
Hello.
Hello.
Hello, sir. Thank you very much, sir.
Yeah, thank you. Thank you very much. Yeah.
The lecture is very informative and innovative, sir.
Thank you. Thank you
And,
very much. Yeah.
and coming to participants, if you have any queries or doubts and questions to raise, you can put them in the chat box, and sir will be answering your questions. And the feedback form is already sent in the chat box, which is intended to submit your feedback, and lecture content and PDF will be available in there. Thank you, sir. Thank you very much.
So we have a question from Mr. Kiran. Uh, maybe sure, but I saw the question now. Is in case of sedimentary soft deposits like in Uttarakhand, which type of system is more suitable? So what I would say is when we are talking about the location of Uttarakhand, there are it's a very high mountainous range, and as of now we do not have wide roads and good connectivity to those locations on the upper hill specifically, so that we can transfer the TBMs on those locations. We need large carriers to transport the machine. We break the machine into various parts. And as far as I know, Himalayas and Uttarakhand are not that well connected with wide road networks to transport the machine right as of now. So we have no other option but to go for NATM tunnels. And and there is one more thing. Maybe if the tunnels are longer than 5 kilometers, I would say approximately. In that case, uh, the cost of buying a TBM is justified by the progress that we achieve by the construction of tunnel by TBM. So if there is a tunnel project where we have more than 5 kilometers of tunneling, and that is feasible to transport the TBM, I think then only we should go for a TBM construction method. Otherwise, we should go for NTM construction methods, which is very much the case for the location of Uttarakhand. We have another question from Narendra. Narendra has said that any case history in India of NATM or TBM success and failure stories. Actually, there are many. There are many success and failure stories for each project. If you would look into, there are many blogs available on internet, and there are many videos available on internet discussing those. Um, even for Mumbai Metro project, which is going on right now, you might see many success and failure videos and blogs if you search on Google. We have from TAIYM, Tunneling Association of India Young Members, we have our YouTube channel and a blog on WordPress, and there are many stories shared by young professionals like me from their projects that they have done. I was involved in Mumbai Metro projects as well, where we were doing many good activities. We did the longest single TBM tunnel. I designed that tunnel, and it went through the highest building of India, and we successfully did it, which is a success story. And we definitely had many challenges in between. The ingress of water was high at times. At times, we found that settlements were higher because the geology that we expected was not the geology at all the locations. There were variations, and there are many such challenges you can find for Delhi Metro as well. In Delhi Metro, there were damages to the buildings. The TVMs got stuck. DMRC has published all these stories. It can be searched from their website as well. And I really appreciate when we are curious to about know such stuff, and this is what makes us better professionals by learning from our good and bad experiences. Moving on to the next question from Sayantan. Does the blasting during NATM turning affects the adjacent liners and rock holds? Yes, yes, of course. But you can always plan how to do the blasting. So blasting is a specified, is a very niche engineering branch as well. So there are experts in blasting who design blast in such a way that if required, the vibrations will not be felt at all, and there may be no disturbance to the adjacent liners and rock codes. But in general, uh, where the project is not, the location is not that sensitive, we may go for cheap blast patterns and cheaper blasting practices as well, because it saves times, and it does not have it saves resources like time and cost, and it does not have any negative impact. So it has to be assessed from the uh, location of the project and the sensitivity of that location. We have another question from Siddesh. For India, which is better, sir? Either NATM or SCL? Well, what I would say is we follow a combination of both NATM and SCL. In urban tunneling, such as metros, uh, I'll give example of Mumbai Metro, which I designed, uh, where, where we actually followed NATM principles while we were doing the primary support. And when we did the secondary support, we followed SCL. So that means while doing NATM construction, the primary support and excavation, when it was done, we followed that all of the load will not come to the supports themselves. But when we did the secondary lining, we assume that all of the load will come on the lining. So because the such few systems are so sensitive, because if there is any scope that the secondary lining fails or is inadequate, then the effect of that will be on the surface. And Mumbai is a very crowded city. It may lead to loss of life and property. So that's why we have to understand that whatever we do, we have to consider the project aspects and the aspects of the people who are associated with it. For example, on the other end, if we are doing hydro tunnels far away in Himalayas in remote locations, then I would say we can go for NATM process, NATM guidelines for sure, and without even thinking about what how it affects, because there are hardly any habitations around it. And if we are making any temporary tunnels, we should go for we would like to save money, and we would like to go for cheaper tunneling practices rather than the expensive ones. And other factor could be geology. Like if we are tunneling in clay, it's difficult to understand how clay will behave in long time of 100 to 120 years, and it is better to go a little conservative and provide more support uh, than than taking a risk of going for a lesser support. So it's all varied. It all varies with the each project. What is the requirement of each project, which makes tunneling so much interesting, because there is no simple answer. There are always many various people, various experts from various fields, and then we come to a reasonable conclusion. Now I think we have another question from. No, I think we have done the question from Sudesh. So I'm assuming this is all. This is all the questions we have, and thank you very much for your kind attention and being here uh, to discuss and to listen to what we had to share with you. And I hope a better future for you and success in your professional careers. Thank you very much. I would like the organizers to uh, please take over. I think we have had all the questions now.
Good afternoon to all of you. I'm thankful to the speaker, Mr. Nirmal, and participants. So I will declare the session is end. So thank you, Ananda. We'll meet once again on Monday evening 6 p.m. Thank you. Thank you, sir.